Hello everyone, here is Anton Kulchitsky from Coupi Inc. And today I'll show you a little video that I made just to demonstrate some features of Polyphysica. And I've chosen a little project of interacting particles in a fluid. So essentially I'm going to show you the example of the flow around the cylinder and the particles that of different kind that floating within that flow. The particles density is equal to the fluid density, so there are not going to be any buoyancy. Particles are not going to sink or raise. So the simulation looks like this. We generate particles here of different kinds, and then they are moving through the fluid, interacting with the cylinder and with each other, and then moving further. So here is the simulation again. So as you can see, the particles interact with the cylinder with some increased pressure in front of it and just behave as expected. So you can do different simulations like this, interacting particles and fluid in Polyphysica by different means, but today I would like to show you a very specific way, very unique way for Polyphysica, when we use built-in capability of lower control functions. So now let me get back to that little presentation I prepared, and I'll talk about the model of the flow that I've chosen for this specific example. So I want it to be very, very simple and basic. So I've chosen very classical problem of the inviscid and incompressible liquid flow around a circular cylinder, where we have an infinite space, the cylinder in the middle, and the flow with the velocity u in an infinity and pressure p0 in an infinity. And we'd like to restore the velocity and pressure field. To do this, we can just, as we apply very standard continuity equation and figuring out that the divergence of the velocity is 0. So there is a stream function exists where you can restore the velocity. And because the flow is curl-free, you actually find out that the Laplacian of the stream function is 0. Very simple boundary condition on a border of the cylinder and actually in the infinity. And you can quickly find an analytical solution in polar coordinates. And then restore the velocity field from this expression. Using Bernoulli equation, you also receive the expression for the pressure. The solution looks like this, and for more details, please take a look on Wikipedia for this specific article, Potential Flow Around a Circular Cylinder. And these pictures are taken from there. And you have the solid lines here, dark solid lines here, showing the stream function, and the potential of the velocity is shown with white lines. The pressure field is showing with colors, red being higher than the pressure in infinity and blue is lower. And here you can see the velocity field depicted with arrows. So that's what we essentially have. The last part is actually how particles interact with the fluid. Essentially, you have different forces acting on the particles in the fluid, and you can split them in drag force, the force due to pressure gradient, the inertial additional mass force, the other forces that may include the lift force of different kind. And for this specific simulation, I decided just to limit ourselves with drag force and gradient pressure force. For the drag force, I also use a very simple Stokes linear drag force model, which is true for pretty low Reynolds number, very low actually Reynolds numbers, but it doesn't matter in our case. This force tends to make the particle velocity be equal to fluid velocity. So try to reduce this difference between these two velocities, and it's directed along the difference of the velocities, which is shown in this picture. Another force that we will consider is a gradient pressure force, and this force happens due to the pressure gradient. It's essentially when to receive the force that is acting from the pressure from the fluid to the particle, you integrate over the surface. And if the pressure gradient doesn't change too much on the scale of the particle size, then essentially this integral can be transformed just very simple to the product of volume by the particle gradient. In one of the forces that appears from this gradient force is, for example, buoyancy force. When you have vertical pressure gradient, hydrostatic pressure gradient, then this formula exactly gives you Archimedes' law. So how do we do this in Polyphysica? Switching back, and now let's look carefully here what's happening. So in Polyphysica, you have a special facility known as control functions. And the control functions is a simple Lua script that does specific job. In our cases, we use, they're all a different kind of these control functions in Polyphysica. And here we use just two functions. One function is an init function, very simple function that runs just once before the program runs, and where we specify the global variables for the fluid density, for velocity and infinity, the radius of the cylinder, and the drag coefficient. That's what I've done here. Very simple code. And another code that is called when necessary. It's called when the particle is moving, and it adds up the forces to the particle here. Here you can see the header part where I calculate some basic values, then the pressure force part where I calculate the pressure force and add it to the body force. And it's for every physical body in the system that uses this function, and the drag force as well here. So we have two forces just coded directly from the formulas that we derived before for this specific stream. But of course these values like velocity field and pressure field can be imported from the outside sources, and this is one way to do coupling with all the different kind of physics. It can be fluid dynamics like here, it can be electrostatics, can be heat transfer, and many other examples. So I've chosen here a non-trivial but very simple example of fluid dynamics. So we can see it from different angle here as well, like let's getting closer. So we will see how pressure force work just in front of the cylinder. We will see the particles coming here and interacting with the cylinder. So particles coming, they feel the pressure in front of the cylinder. Larger particles are more sensitive because their volume is larger, and particles are bouncing back and forth here. So very nice and simple simulation. Runs very fast for this that few particles, and very easy to set up in Polyphysica. So this is it for today. Thank you very much for your attention, and have a wonderful day.